Hello everyone, in this video I will be explaining to you why we use inclusion-exclusion principle in deriving the formula for derangements. For those of you that do not know what derangements are, let's explain it using an example. Let's say you really wanted to get into an IIT but you couldn't for whatever reason. And so now you want to get a job at an IIT so you can experience the IIT campus, albeit not as a student. So what you do is you get a job as staff in the hostel management department, and your job is to manage hostels. More specifically, you are assigned, rather tasked, to manage the boys hostel for first years. The boys hostel for first years has n boys and n rooms, exactly n rooms, to accommodate those n boys in the entire campus. So after the first semester, everyone, every single one, wants a new room. They don't want to be in their room anymore. They're tired of it. It's very annoying. Everything is bad about the room. So they want a new room. And now you need to assign them new rooms such that no one should end up in their old room and everyone will be happy then. So what derangements actually is the total number of ways in which you can do that. So the condition is that boy number 1 should not be going to room number 1. He can go to room number 2, 3, n, anywhere in between. Anything is fair game, excluding 1, of course. And boy number n, he wants to go to 1, 2, 3, anything that is less than n. He's tired of being in the last room. He wants a lower numbered room. So in how many ways can you do this task is the question we need to answer. So let's answer that. Firstly, we need to find the total number of arrangements. The total number of arrangements can be given by n factorial, of course, as we know. What the total number of arrangements actually means is you take a boy, you assign him a room, and it doesn't have to be a new room or an old room. It can be any room, and that's fine. Now, of course, that's not fine because no one's going to be happy if that happens, if they once again get their old room. So we are going to have to remove those cases. So let's take a case where at least one person has complained against you that you are bad at your job and you have assigned them their old room again. I would like to put some emphasis on the words at least, as in it can have 2 people or 3 people or 4 people. Now, maybe to some of you it makes sense that shouldn't the total number of arrangements subtracted where at least one complaint happens is just the answer to this question? And the answer is it's not, because at least one complaint, this case, actually counts some events more than once. And we will have to remove that later, or rather add them back, because we are subtracting this case. So this can be done, at least one complaint can be done in NC1. So we're choosing one boy from n boys. Then we're arranging the rest of them in n-1 factorial ways, as we know. And then these two are dependent events. So we are multiplying them. Now let's come to case 2. At least 2 of them have lodged a complaint against you. And this is going to be done in NC2, and then again we arrange the rest of them, n-2 boys, in n-2 factorial ways, and then we multiply them because it's dependent event. And then these cases will go on and on all the way up to all n complaints have been lodged against you, like as in all n of them, all the boys have complained that they're still in the same room, you did not do anything. And that can of course be done in only one way. So now we will calculate dn. dn is how we denote derangement of n objects. So first we take all possible arrangements n factorial. Then we subtract the first case because we are trying to remove them all, right? But then we realize, okay, now I don't have enough cases. I should be having more cases than this. And what we have to do then is we have to add back the repeated cases that were subtracted by mistake. So So we have to add them back. But this too has a problem because this also has repeated events. It has calculated a lot of events more than twice. And so now we will have to subtract another term, which is going to be nc3 times n minus 3 factorial. And this series or pattern will go on all the way up to minus 1 to the power n ncn times 1 factorial, which is just going to be 1, as I said. Now, this can now be simplified to this, which you have maybe seen, or if you haven't, this is the formula for d of n. And as to why this is minus 1 to the power n, if any of you were wondering, if n is even, then the last term will be positive, and minus 1 to the power n even number is, as we know, positive. And if n is odd, then the last term should have a negative sign. And as we know, minus 1 to the power odd number is always minus 1. So that's an easy way of just changing the sign. Now, here's the big question. Why do we even use inclusion exclusion? Shouldn't it be something like this, where we have n factorial, this whole set is n factorial, this whole rectangle, and then this is a subset, which is where at least one has gotten the wrong room, and then that has a subset where at least two. I mean, shouldn't at least two of them getting the wrong room, rather the same room, have to be a subset of them getting at least like one of them getting the same room? And the answer is no, because let's take an example. Let's say at least one of them has gotten it, just one of them has gotten it wrong, okay? Just one is going to be boy number 1. He gets sent to room number 1 again for the second semester, and that's a case we have to take out. But it could also happen that boy number n minus 1 and n, both of them are going to have the same room as their last semester. And as you can tell, that's obviously not a subset, because in the case where one got his same room, then that does not happen in actually the second case. So this is a wrong diagram. This is the wrong Venn diagram. This actually is not how it would look. And now let's explain how we are getting those repeated events. This is person number 1, boy number 1, and you call him to the office and you ask him, did you get the same room again this semester? And he's like, yes, please change it, I can't bear this anymore. And then you send him out, and that's that. You are not going to do anything. So now you ask boy 2 if that also happened with him, and he says, yes, it did happen with me. But let's consider that this is the same case. Everyone else got their rooms right. Just boy 1 and boy 2 had their rooms messed up. That is, they got the same room again. So when boy 1 says that he had the same room, we count that as 1, right? Now we also have boy 2 saying that, so that's 1. However, what if you tell them both to come in the room at the same time, and then you ask them that and they say yes? Then that's also 1. And the thing is, both of them saying yes actually just represents one event. So what we need to do actually is we need to subtract these. We need to subtract from this value to this value 1. This actually also holds for bigger values. Like when you're going to get like 3 people, groups of 3 people and 4 people, this will hold. That's how this works. And that is why we use Inclusion-Exclusion Principle in when deriving the formula for derangements. I hope you understood and I hope you enjoyed the video and it was explanatory and you understood something. Thank you for watching. I will meet you in the next one if I make a next one.